Three, two, one. Good evening, everyone. We have a jam-packed Burchard 118. Should I start again? We're good? Okay. I saw a concerned look on our cameraman's face. All right. Welcome, everyone. This is the Fall 2018 Final Exam Review for E232. We're jam-packed here in Burchard 118. All 10 of us are here. So I want to begin, as always, by thanking SIT TV and their support. And this is Jesse, who is our cameraman tonight. So Jesse, thank you. Jesse had a run here tonight from his co-op to get here on time, and I thank you very, very much. My studio audience, ask questions, because there's probably someone at home who has the same question you have, and they're not able to ask that question. All right, we're going to go over a final exam that is posted on the course website, which is the spring 2014 semester. I think this is a good exam to go over. So we're looking at the spring 2014 final exam, and it's posted on the course website. So let's just dive right into it. All right, so I'm going to scroll down. So let's not look at the solutions yet. I'm hoping that none of these problems surprise you. Okay? I'm hoping that none of these problems surprise you. All right, so you're given a sensor, which can be modeled as a first-order sensor. And the input to this sensor is applied at t equals 0. And I say that it's a constant input, so the input is a constant. And it has a value of 55 for t greater than 0. And now the initial reading of the sensor is minus 12.7. The time constant is given as 4.6 seconds. So I'm hoping all of this looks very familiar to you, and you say, okay, what am I asked? Part A, determine the output of the sensor 11.3 seconds. So at t equal to 11.3 seconds, determine the output value of the sensor. Now, as we're filming this, right before I came here tonight, I was working on my circuits final. And, you know, you probably remember in circuits we had first-order systems. So I'm hoping all of this is like old news to you, that you fully understand this. So since it's a first-order system, I know that the output y of t is tau times the x of t dt plus x of t. Now, y of t, oh, you know what, my colleagues? Please forgive me. May I write something on the board here? This is not, it's not that it's incorrect, but the notation is different than what I've done. Forgive me. My colleagues, let me put any concerns you might have to rest if you were to review this. The input in class I've always called x of t. And Alexandra, the output is y of t. I don't know what possessed me during this exam, but I wrote it backwards. Okay, so please forgive me. Christina, what I should have written is that the output, okay, so what we have is tau times dy dt. So forgive me, it's a little different than what I have there. We're going to get the same answer, but I just want to use notation you're familiar with. Equals x of t. And in this case, x of t is the input, and x of t is 55. And this is for t greater than 0. For those of you who are looking at the screen here or looking at the exam, I flipped the y's and the x's. And I'm sorry, I didn't mean to do that. So this is how it should have been written, where y of t is the output. So I say, all right, what is the initial condition? The initial condition is that y at t equals 0 is given to be minus 12.7. Now, the solution to our first-order differential equation, and here I use the correct notation. So right underneath where it says solution to our first-order differential equation, there I use the right notation. The output y of t is k e to the minus t over tau plus the input if it's a constant. In that case, it's 55 because our input is a constant. So if I could just go back over here to the screen, we now have the equation in correct notation. Y of t is k e to the minus t over tau plus the input, the right-hand side, the particular solution. Am I doing okay? Thanks. So if I just scroll down, what we then have is we can now use the initial condition to solve for k. So y of t at t equals 0 is minus 12.7. And that's equal to k e to the minus t over tau plus 55. And what I get is minus 67.7 for k. So the first thing I get that's of importance here is this equation here. And it's the right notation. The output, y of t, minus 67.7 times e to the minus t over tau plus 55. So now we've got the equation that defines the first order sensor. And what we're asked is, tell me the output of the sensor at 11.3 seconds. So I just have to plug in 11.3 into that equation, and we got the answer, 49.2. Now, I'm hoping you think this is easy because it was meant to be easy, just to get you warmed up, doing some stretching exercises before the final. So hopefully you see this problem and you go, yeah, I got it. My studio audience, any questions so far? Christina, tau was given. Christina's question is, where did we get tau? I think that was in the last line of the problem statement, Christina. Yeah, right above. Okay, so it says tau is 4.6. So you're given all these numbers, and it's just a matter of plugging in. So we say, all right, part A looks good. Now we go to part B. Part B says, determine the time it will take the sensor to reach 90% of its final value. Now, Ryan, if someone makes a mistake in part B, it's because they don't know the final value. This first order sensor is a rising exponential. And I just want to go over here to the board to point out that, and Christina, maybe you can help me. The input is 55, so I'm going to draw that here as a dotted line. And Alexandra, this is y of t versus t. Now, I think the initial condition was minus 12.5. So that's somewhere here. This is minus 12.5. And what happens is we exponentially rise. And we exponentially rise to the final value of 55. So the key to answering part B is to note that the final value is 55. Alexandra. Negative 12.7. Alexandra, thank you so much. So thank you. So the initial condition is minus 12.7, and the input is 55 at a constant value, so I know it's a rising exponential. Now, if I go over here to the screen, I start out my solutions by saying the key observation is that we have a final value of 55. So what we want to find out is how long does it take me to reach 90% of 55? So I think, again, this problem isn't that bad. So 0.9 of 55 is 49.5. And I then just plug that in to the left side of our equation, and this is the key equation here, and we solve for t. So this gives us the time to reach 90% of the final value. And it turns out this is usually an important measure of the sensor, because we're looking at a sensor to be fast. So how long does it take to reach, let's say, 90%? That's a number that's commonly chosen. So you'll see in my notes here that I solve this step by step. We take the natural log, and we get about 11.5 seconds. Our colleagues are copying this. I'll give you a moment to look at it. All right, so I say, all right, that's part B. So we have that done. And I did a quick check, just plugging in the value of t, Christina, to make sure that I got the left-hand side equal to 49.5, and it does. Now, I now throw in a little bit of Chapter 11. Okay? Chapter 11 dealt with errors and so on. So we also had a ramp input to our first-order system. Now, a question I typically get is, can we just write down the answer for this type of question, or do we have to prove it? You can just write down the answer. So I think this is something that you should know. It says here, the constant input is now disconnected, and we put a ramp to the first-order sensor. Now, I'm hoping you remember that the ramp has a systematic error. As an input, pardon me, I should be more specific. The output of the first-order sensor has a systematic error if the input is a ramp. So I'm just going to go over here to the board. Let me erase what I have here. And you might remember that this is T, and this is the output of the sensor. Now, in our lectures, we drew a line like this that was described by A times T. So it was a ramp function with a slope, a constant slope. And we said that was the ideal output. That was the ideal output. Now, the first order sensor with a ramp input has a transient, and then I'm having a hard time drawing this. These two lines are meant to be parallel after a certain point. So notice we always will have an error. Now, how do I measure the error? Suppose this is time t1. What is the error at time t1? It is the vertical distance between the ideal response, shown in black, and the actual response, shown in blue, below it. And it turns out that this vertical distance, as it were, this error function is tau. And if I go back over here to the slide, I can just write down the answer. The answer is tau. Okay? Now, can anyone help me out? If I asked you the error, what's the next thing I'm going to ask you? The other thing that we discussed with the ramp input to a first order system. There was the error, the up and down. And what was the other thing? Alexandra, lag time. Perfect, perfect. So if I can go over here to the board, I'm going to erase tau, Alexandra, because it's in the way. I'm erasing tau. And now we're looking at, and I'm going to have to draw the line up a little bit more here. I'm looking at if this is the actual item we're trying to measure, and at time t1, this is my reading. The question is, how long does it take for me to catch up to where I am right now? Okay? So there's going to be a delay, and that's the left-right, the horizontal distance. And it turns out this is given by, I think, another easy quantity. Anyone remember what it was? Alexandra, you're smiling. My colleagues, Alexandra, give it another shot. Perfect. This here is the lag or delay, and it's A times tau. So just to see that I make sure I've written this correctly on my answer key, this then becomes A times tau. My colleagues, I'm embarrassed. Have I mixed it up? And plus, this is being filmed. I'm going to be fired. Did I make a mistake? Have I gotten things backwards? This is what happens with me having an early review. I'm best after 9 p.m. at night. I'm drawing a blank. You'll have to forgive me. I wrote the answers differently. I think I wrote it backwards. Tell you what, Jesse, I'm going to just compare to the lecture notes here. I'm so sorry, my colleagues. Wow, that's a loud sound. I don't know how to stop it. My colleagues, I am so sorry. I heard people yelling at me. Yeah, look at this. I got it backwards. Professor Miles, this is bad. I'm just all confused. Jesse, I'm sorry. My colleagues, you can take everything I said and just flip it. So Christina, I need to correct myself. So it turns out that, as pointed out here, the left to right, this is slide 17. The left to right is tau. So the lag, the delay is tau. I am so sorry. And Christina, what then is the error, my colleagues? No need to switch the camera. I'll be right back on camera. The error, the instantaneous error, is given by A times tau. My colleagues at home who were throwing things at the screen, I'm very sorry. The error is A times tau. Thank you. So what we have is, let me now clarify. The delay is tau, and the error is the slope of the input, which is A times tau. Have I done okay? Have I recovered? All right. So I now come over here. Let me close these lecture notes. And now I agree with what I wrote. So here it says the time delay is tau. So the time delay is tau. And the instantaneous error is A times tau. Sorry about that. Veronica, my colleague in right field, we're good? So that takes care of parts C and D. We're now on to problem 2. And problem 2 is from chapter 7. So what I'd like to do is, first of all, just erase the board. And then I'd like to read the problem and draw what the problem is telling us. Also, my colleagues, there's 3 things in the back of my mind that's causing me to get distracted, although that's not an excuse for making an error. I'm just going to write them down here. I want to say something about the binomial distribution. I want to say something about chapter 11. And I want to say something about Internet of Things before the night is over. So I put those 3 things on the board. All right, so it says here on the screen, we have a sensor. And what happens is the sensor has some data. And I'm now on to the fourth line of the very top of the problem statement. It says the remote sensor is connected to a wireless network, and the received signal at the control station is then filtered, amplified, and converted to a digital signal by an AD converter. So what I'd like to do is to just draw that. If I can draw it, I think I can help solve it. So I'm looking at the end of the third line. It says here, what we have is, starting at the beginning, you're given a measurement system to remotely measure air quality. The remote sensor is connected to a wireless network. So we have a sensor, and it is connected to a wireless network. We'll just show it as some kind of cloud. And then from there, the received signal is then filtered, amplified. So we go into a filter, an amplifier, and lastly, an A to D converter, A, D, C. And then we get the output. Now, as you might remember in Chapter 7, each of these items introduce an error. What we'd like to do is kind of add up the errors to figure out what is the total uncertainty in the final answer. So heading back over here to the screen, we're given a lot of information. And I think a problem like this is just, careful reading of the problem. So notice in the answer, I have sensor to wireless network to filter to amplifier to A to D converter. Now notice I wrote down here all the standard deviations that were given in the problem. So I go back here and I say, okay, what do we have? It says here, reading this paragraph right here where I have the number 4.3, it says a large number of tests were made on the sensor, and the standard deviation of these measurements was 4.3. So what I did in our lecture, I came over here to the whiteboard, and I said the standard deviation for the sensor is 4.3. Now I'm going to continue reading the problem. Next paragraph down, it says, for the wireless network, a large number of tests resulted in a standard deviation of 1.7. So the standard deviation is 1.7. I then go on to say the A to D converter, let me read the filter, sorry. In a separate test of the filter, a large number of tests resulted in a standard deviation of 1.3. Now, I remember, my colleagues, in Chapter 7, when we were discussing this, when we say a large number of tests were done, that means it was done before the system was put together. So someone tested the sensor in the lab, someone tested the wireless network and the filter. And so I got the filter. Now it says the A to D converter may produce a random uncertainty of 2.5. Here's what I'm hoping, if you go back over Chapter 7, you'll remember. Notice, up till now, we had standard deviation, 4.3. Standard deviation, 1.7. Standard deviation, 1.3. Random uncertainty, okay, of 2.5. Now, it turns out, you might remember that for a 95% confidence interval, the random uncertainty is related to the standard deviation by a factor of 1.96. We got that from the Gaussian table. And the author says, forget 1.96, just remember 2. So what we do is we say, great, what then happens, and I'll show you, I have it written down in the solution here, the standard deviation of the A to D converter is 2.5 over 2. Let me pause. How am I doing? I see a question in some of my colleagues' eyes. Here, it's 2.5 over 2. I'm looking at my colleague's eyes. Do you happen to remember this formula? Plus and minus z alpha over 2 times the standard deviation over the square root of n. This quantity is the random uncertainty. Now, how many measurements are we now making? 1. So n is 1. So this is the random uncertainty. And this becomes plus and minus z alpha over 2 times the standard deviation for n equal 1. Now, we're told that the standard deviation was 2.5. And we're told we made a lot of measurements that we assume are independent and identically distributed. And a lot, I think that's more than 30. So we can use the Gaussian table. So if you went to the Gaussian table and looked up 95% confidence and said, what is the value of z sub alpha over 2? If I remember correctly, it's 1.96. So the author says, let's use 2. So the standard deviation right here is the random uncertainty divided by this number, which we're going to approximate as 2. That's how I got 2. Veronica, Alexandra, how did I do? Correct. If you had a different confidence interval, you wouldn't divide by 2. That's not going to happen. In Chapter 7, the author says we're going to stick with 95%. So I'm going to follow that. So we're staying with 95%, which gives us the factor, the z sub alpha over 2 of approximately. How am I doing? Am I doing all right? Okay. So I now look here and say, okay, I understand where I got all of these. Now, I'm hoping you know what's going to happen next. We're going to add all the s's. But how do we add them in Chapter 7? RSS. Something about squaring them. Remember, read it backwards. RSS, we square, we sum, and we take the square root. All right? So that's what's coming up next. So I'm looking at the screen. I have, did I miss a number? 1, 2, 3, 4, 5. 1, 2, 3, 4. I forgot the standard deviation for the amplifier. Forgive me. The amplifier, it was in the problem. I didn't read it. The S for the amplifier is 1.5. Now, there are two sources of error. There's the random, the uncertainty error, which is what we're capturing here with the standard deviation. And then there's the systematic error. So I say, all right, are there any systematic errors? Turns out there are. So we're going to get to that because the first thing says determine the random uncertainty of the measurement. So I say, okay, the random uncertainty is going to be determined by these standard deviations. Then I'm going to get to the bias or systematic error. So these are random uncertainty. And how do I now calculate it? I add up the standard deviation. And I do the addition using RSS. And reading it backwards, it says we square, and then we sum, and then we take the square root. So I take these 5 numbers, square them, add them, take the square root, and if I've done it right, we get 5.185. Now, the question is not asking for the standard deviation. If I go back to the question, it says, what's the random uncertainty? What have I now calculated? In this calculation here, I've calculated the standard deviation. So I'm saying, wait a minute, I know how to go from the standard deviation to the random uncertainty. So I say here, because the number of measurements to determine the standard deviation was large, we can now go back and use the same formula we had before, where this is the random uncertainty. And it's now plus and minus t sub alpha over 2 or z sub alpha over 2 times the standard deviation over the square root of n. So I say, okay, let me just write that over here. So the random uncertainty, which is what we're looking for, is plus and minus z sub alpha over 2 times the standard deviation over the square root of n. N is 1. I'm making one measurement. Now, the author uses t here, and that's fine because he's saying we're going to go to the student t table where the degrees of freedom is infinite. And Ed, the degrees of freedom infinite, the student t table equals the z table, the Gaussian. So whether you write that as t or z, if you let the degrees of freedom go to infinity, which is assuming a large number of measurements were made to determine the standard deviation, we say, great. So it turns out, going back to Alexandra's point, the z alpha sub 2 or the t alpha sub 2 or sub alpha over 2 is 1.96, which we're going to approximate again by 2. So we say, all right, what do I now get? The random uncertainty is twice the standard deviation, which is 10.37. That's the first part of the problem. How do we do? And again, this is a Chapter 7 problem. So far, so good. Let's go on to part B. Part B says, tell me the systematic uncertainty. So what we've just covered is the random uncertainty. Now, there's a systematic uncertainty, and it turns out the only element that has a systematic uncertainty is the sensor. So I go back up here and I say, wait a minute, how do I know that? And this was given in the problem. Now, we didn't cover these 3 specifically in Chapter 2. But when you get a problem like this on the final, all you have to recognize is that these three items, sensitivity, linearity, and hysteresis, are systematic errors in the sense. So these become systematic errors. So, for example, the first one is 0.25% plus and minus, a full scale. Now, another place where colleagues make a mistake, but I don't want you to make this. The bullet item on top says the range is plus and minus 3,000 on this sensor. So it goes from a possible reading of minus 3,000 to a reading of plus 3,000. Okay? However, full scale is what? I think there's two choices, 3,000 or 6,000. What's full scale? 3,000. Full scale is the highest you can get. Full scale. Well, full scale in this course is 100. So full scale is the absolute maximum reading. It's not what we call 6,000 going from minus 3 to 3,000 to plus 3,000. So don't make that mistake. Full scale is the maximum reading of the sensor. And in this case, full scale, 3,000. So what we have here is another great question from Alexandra. Help me out. If I remember correctly, and you can help me out, I think we call that the span, or sometimes just call the range. Okay, the range of possible outputs. But full scale is the max. And the sensor manufacturer typically states the error as a function of full scale, which is the maximum value out. So now we get 0.25% of full scale. And then there's other numbers, 0.15 and 0.1. So what I now do in part B of this problem, and I'm hoping this looks very familiar because we did something very similar just a few moments ago. First thing I do is I calculate the three components of systematic error. Now just be careful, 0.25% is 0.25 over 100 times 3,000. And you do that for the other two items, and we now get three different numbers. So my colleagues, I'm going to walk over here to the whiteboard, and now I'm going to squeeze in the letter B. The letter B here means bias or systematic. So there's three errors. One is 7.5, the other is 4.5, and the other is 3. Now, what do? I'm going to have to add them together. And going back here, you'll see on the screen how we then add them. And hopefully this is very familiar. So we show on the screen here that what we have is the addition of three items. So for those of you at home, you should be able to look at your document. If I go over here to the screen, we have each item squared and then added together, and then the square root, and we have a systematic error of 9.25. Now, the last part of the problem, I think, that I ask you is what's the total error? Now, the total error is going to be, the total uncertainty is now going to be an addition of both. The addition of the random uncertainty and the addition of the systematic uncertainty. How do I add them? RS, okay? So let's see. I think that's the next part of this problem. Okay? The total uncertainty, when I said error before, I should have said uncertainty. The total uncertainty is now using the author's notation W for total. I don't know where he got W from, but we're going to go with it. And it's the sum using RSS of the systematic uncertainty and the random uncertainty. So now you've gotten the right answer and you got full marks. But here's something else. I want you to understand what this means. Okay, you've done all this hard work, and I want you to say, okay, what does this mean? Going over here to the board, I'm now getting a number here. Right? I mean, the sensor has measured something, gone through all of this, and I now get a number. So let's suppose the number is, 937, whatever that's reading. That's what it measures. What we really should say, it's 937 plus and minus 13.9. See, that's the uncertainty. And that uncertainty is a function of, Veronica, of the uncertainty in each of these elements, the sensor, the network, the filter, the amplifier, and the A to D converter. Yet another problem done. How do we do? All right, everyone. Thank you. Here we're doing it. Now, Ryan, I don't know what I should have just said the probability of each sensor working is 0.8. No, I didn't do that. I wrote it out. I don't know what, Professor Miles, I don't know what this was like. I look back on this and I say, this is crazy. Must have been not at night. Right. I could have just written that all sensors working with a probability of 0.8. But I don't know, I had to write it down, cut and paste each one. All right. So there are 6 sensors in some network, and it says here, determine the probability of a system of sensors working properly. Now, before we look at the figure, and I've met with some colleagues already about their exam 2, and this came up. So I just want to review something very quickly that's very basic, okay? So I'm going to run over here. I'm going to say, okay, what's so basic that we have to look at? My colleagues, if you're given 2 sensors in parallel, what is the probability of this system working? Now, this doesn't sound too bad, but there's an easy way and a hard way. The hard way says there's 3 ways in which this network of sensors can work. First, both sensors are working. Secondly, 1 works and 2 doesn't. Thirdly, 2 works and 1 doesn't. So you can solve this problem 3 times and add it up, and you'll get the right. Now, the only problem is, what would happen if I were to give you 10 sensors in parallel? You now have to look at all possible ways that this is going to work. I claim, Ed, that's going to be. So I think the easy way is called for you. So the easy way says, all right, wait a minute, forget 10. Let me just solve 2. Okay? So the probability of a sensor working, let's say that's P. In our case, that's 0.8. But let's keep it as P for now. What's the probability of this parallel sensor combination not working? The only way this doesn't work, the top one doesn't work and the bottom one doesn't. So the top one not working is 1 minus P. The bottom one not working is 1 minus P. So the probability of this system not working is 1 minus P squared. Now, I'll leave it to you. Might be obvious. If I had 10 sensors, the probability of 10 sensors not working, 1 minus P to the 10. So I got the formula. So now if I were to ask you, what is the probability of this combination of 2 sensors working? 1 minus P squared. That's it. Okay? I think if you know this, I can't give you a problem you cannot solve. You're going to be able to solve everything. So what I now need to do is to slide to the end of this exam. And there's figure 1. Now, I got to view this by rotating, and I think I want to rotate it clockwise. Now, my colleagues, I need your help. I want to make sure I don't make a mistake here. Now, sensors 1 and 2, what is the probability of those 2 working? I should be more careful. What's the probability of those parallel sensors, 1 and 2, of that part working? I think that is 1 minus P squared. Right? That becomes the parallel combination of those 2 sensors. Am I doing okay? Now, what about the next 2? Same thing. Alexandra, am I doing this right? That's the probability of it not working. Probability of it working. Now I come down here to the bottom, and I get 1 minus P squared. So my colleagues, in terms of a calculation, this is what that now reduces. Jonathan, so far so good. I now put in P equal 0.8, and I'm going to get numerical values. So let me now go back to the solutions where we'll see that calculation done for us. I need someone's help. Now, let's see if I can get these same numbers. Does anyone happen to have a calculator? Jesse, let's see if I can. I know all this is written down here. Now, this is the probability of this 2 sensors working. This is the probability of these 2 sensors working. So far, so good. All right. So what I want to do is I'm going to get 1 minus 0.8 squared, and here I get 1 minus 0.8 squared. Now, before we shout out what that number is, that's the probability of this sensor working, and that's the probability of this sensor working. My colleagues, what's the probability of the upper path working? The only way the upper path works is if both sensors work. So I take this probability, the probability of it working, and I multiply it by the probability of this sensor. That gives me the probability of the upper path working. Jesse, I have my fingers crossed. You get 0.9216, or have I? Oh, I hope I didn't do so. 1 minus 0.8 squared, 1 minus that. Take that quantity and square it. 0.9216. We got it? I'm concerned you don't have a confident look on your face. Have I? Right, so So help me out. What is this number here? What's 1 minus the quantity 1 minus 0.8 squared? 0.96? So this whole thing is 0.96. Jesse and Alexandra, this should also be 0.96. That's the probability of these grouping of sensors working. Now, what's the only way that the whole upper path can work is if both of these sensors work. So according to my calculation, if you take 0.96 and you square it, you get 0.9216. Okay, I see a thumbs up and a nodding head. All right, that's the probability of the upper path working. Now, Christina, likewise, the bottom path. The bottom path only had 2 sensors working in series. Pardon me, 2 sensors in series. So this quantity is 0.96. That's the probability of the lower path working. So my colleagues, this is the probability of the upper path working. This is the probability of the lower path working. So what we now have, if I could just simplify this. Veronica, am I doing okay back there? All right. So now I can reduce all of this to 2 blocks. The probability of the upper path working is 9216. The probability of the lower path working is 0.96. Now, going back to a few moments ago, there we had P to be the same. Now they're different, but you can still figure this out. The only way this doesn't work is if the top path doesn't work and the bottom path doesn't work. So this is going to become 1 minus 0.9216. That's the probability of the upper path not working, and multiply that by the probability of the lower path not working. That now gives me the probability that the system doesn't work. My colleague, how do I get the probability that the system now works? Exactly. Now let me just scroll down on the screen, and we should have that. The probability of the upper and lower paths not working, 1 minus 0.9216, and then times the quantity 1 minus 0.96. So we get 0.003136. 1 minus that is the probability of that network of sensors working. How do we do? For Alexandra. Correct. Can I just repeat that? Because Alexandra's question is pointing out we did a pretty good job of understanding how sensors work in parallel. Now, if we were to just look at series sensors, so you have sensor A connected to sensor B, the only way I get from the input to the output is that both of them work. And since they're independent, we take the probability of working for sensor A and multiply it by the probability of sensor B working. So Alexandra, suppose they both had the probability P of working. The only way this upper path works is if sensor A works and sensor B. So it's an and, so we multiply. Did I do okay? All right. Okay, here's problem 4. Now, before we write this down, let me just erase the board. This is now one, let me pick up this eraser, excuse me. This is one of the 3 announcements that I wanted to make. My colleagues, I've already shared this with the colleagues in the room here. There's no binomial distribution on the fund, okay? So we can skip problem 4. I think it's a great problem, but it's not going to be, or anything like it's going to be on the fund. So the first announcement I had over here was something about binomial. The binomial distribution is not on the fund. So we can skip problem 4. All right, we're now up to problem 5. Problem 5 is a chapter 6 problem, the parameter estimation. So we're asked to determine, in this case, something called the average transmit power for a wireless sensor. And 4 sensors are tested. What's important about 4 is that it's less than 30. Okay, so right away, I'm hoping you know that this is a student T distribution. It says estimate the population mean. So I'm hoping you're very comfortable with it. First thing you do is to calculate the sample mean. And you all know how to do that. Just add the 4 numbers together, divide by 4. Next, what we do is we calculate the standard deviation. Now, this formula is on the formula sheet. Now, you might be saying, wait a minute, where's the formula sheet? It's with the exams posted on the course website. So the formula sheet will tell you how to calculate the standard deviation, and you might remember this. It is the term inside each parenthesis in the numerator is the measured value minus the mean. And we square it, so we always get a positive number, and we add them up. Now, because this is the standard deviation of a sample, we divide it by not 4, but 4 minus 1. We do it n minus 1. Once we do all of that, we take the square root. My power of 1/2 didn't fit on the page there. Barely see it. We take the square root of all of this, and I write that down over here. So this now gives us the standard deviation. So now we have the mean, and we have the standard deviation. Now, coming over here to the board, the key formula, and again, this is on the formula sheet, mu. Now, that's the unknown average. If we measured every wireless sensor, that would be what we would get, the mu of the population. We have only measured a sample, in this case 4. So it turns out that the mu is x bar, the mean of the sample. And then there is, what we were just calling random uncertainty. This is the random uncertainty. We didn't use that term in Chapter 6. We saw that in Chapter 7. And this is then going to be equal to the t variable, t sub alpha over 2, times the standard deviation of the sample divided by square root of n. And that's the next formula you're going to see. So that's the formula for estimation of student t. Now, we want to be, how confident? 90% confident. Okay? We want to be 90% confident. Now, just for the fun of it, this will probably be the last time we're going to do it. So let's just do it. Boy, that sounds loud. Here's the formula sheet that you'll be getting, and here is the student t distribution. Now, if I go over here to the board, okay, and I draw the student t distribution, and I pick 2 points and say, okay, if I want 90% confidence, this area has to be 90%. That means the tails here and here together make 0.1. That means one-sided tables, which is what we have, the tail would be not 0.1, but 0.05. And the degrees of freedom, you probably remember this. The degrees of freedom, which is V, is n minus 1. In our case, that's 4 minus 1, which is 3. So now, going back to the student t table here, I go to the degrees of freedom, which is 3, and I scroll over until I get to 0.05, which is here, 0.05. And if I'm doing this correctly, we get 2.353. So hopefully, that's what I have here, and I do. So we get the t sub alpha over 2 is 2.353. And now just plug it into this formula, mu equals x bar plus or minus the t statistics times the quantity s over the square root of n. Now, you can write the answer either way. That's sometimes a question I get. You won't lose points either way. You can write it as mu equals something plus or minus a factor, or you can put upper and lower bounds on mu. Same thing. Doesn't matter how you write it. You'll get, if it's right, you'll get full credit. Student t distribution, how do we do? All right. Now, problem 6. Problem 6, this is a Chapter 4, Chapter 5 question. It's Chapter 4, Chapter 5. So you're given a function f of t, and it's made up of 4 different terms added together. So we have 4 different terms, cosine and a sine, all added together. Now, the 2 highest frequencies are unwanted noise. And the function is to go into a A to D converter to be converted to a digital signal. So we say, okay, first item, the notation. This is where you could accidentally make a mistake, which is going to ripple through the whole problem. Don't want you to do this. So let me go over here to the board. And what we have here is typically a sinusoidal term, let's say sine or cosine, is written as 2 pi ft plus, for example, an angle. That's standard notation, 2 pi ft. Now notice the first term. The first term is 375 pi t. So that means this quantity here is 375. What's f? F is not 375. So what you have to do is say 375 times t. So 375 pi, excuse me, my colleagues, Jesse, I didn't write this clearly. Let me, forgive me here. I should have said this. 2 pi, what I wrote before included pi, so forgive me. 2 pi ft equals 375 pi t. The pi's cancel, the t's cancel, and we're left with 2f equals 75. That means f is 187.5. And do that for all 4 terms, as I did on the top of this page. Now, part A says this function is applied to an A to D converter without an anti-aliasing filter. That means we're not removing the signals we don't want. What's the required sampling frequency of the A to D converter? To answer that question, I need to know the highest input frequency. And the highest input frequency is the 4th term, which is 1375 hertz. And the Nyquist theorem tells us we have to sample at least twice, hence the minimum required sampling is 2 times the 1375. We get 2750. And now I say, tell you what, I think we should use an anti-aliasing filter. Why? Because the problem tells us the 2 highest frequencies are no longer needed. We don't want them. So let me just go back and read that. So Christina, we state in the problem that the 2 highest frequency terms are unwanted noise. So I don't want them at all. So if I'm going to pick an anti-aliasing filter, I want that low-pass filter to let the first 2 terms in, but remove the 3rd and the 4th. And the first 2 terms are captured with the highest frequency of 637.5. So I'm going to remove the 2 highest terms with my low pass filter. So I say, all right, but I have to have the low pass filter let the first 2 terms go through. And it says here, how would you pick the corner frequency of this low pass filter? Now, I'm going to come over here to the board. You might remember this discussion in our lectures. Here is a low-pass filter. This is the anti-aliasing filter, right? And then we go into the A to D converter, analog to digital converter. Now, the highest frequency I want to get through here is 637.5. So the simple answer is to set the corner to that, 637.5. However, that's not good. If you remember our discussion of filters and how at the corner frequency, if I were to look at frequency versus the gain of this low-pass filter, the Bode plot. Now, why am I thinking Bode plot? We didn't discuss Bode plot at all in this course, so don't get worried. I'm making up the circuits final. I'm asking them a Bode plot. So don't worry about the Bode plot. This is the Bode plot of an approximate response. The actual response, you might remember, looks like this. There's a little bit of a curve. Now, this is the corner frequency. It turns out that at the corner frequency, the gain is 0.707. That means we've lost 30% of the good signal, which is typically not acceptable. So what you do is we could, if we wanted a simple way out, pick F sub C to be this. And notice I gave you full credit if you did. But the much better answer is to make F sub C larger. So then you get all or almost all of the good signal through. How we doing? What's the disadvantage of making F sub C bigger than the highest frequency that we want to get through the, or making it, what's the disadvantage of making the corner frequency bigger than the highest frequency? Sorry? It could be, here, Ed, help me out. Ed is taking a lead on this. Ed, you probably have this written down. Ed, I might need your help. So Ed, let's do the simple one, Ed. Corner is 637.5, right? Help me out. Does anyone happen to know what's the next frequency up? The 3rd term. Sorry? 936.5, right? Okay, so here. We come over here, and then we drop, right? Look, how much of this are we getting? Not much. That's a very low gain, right? The problem is we've already started to drop off. Let's draw the same one again. Ed, help me out. Make sure that I make sense on this, Ed. Okay? Here is 637.5. Here is 936.5. Ed, give me a number. What? Maybe 800? So 800, kind of eyeballing it, is here. That's 800. Now, that means I'm flat, and then I drop off. Now, notice, that means I'm flat. Oh, I'm probably getting like 99-point-something% of the good signal. Fantastic. But now what's happening? Oh, wait a minute. I'm getting a lot of that unwanted. So in engineering, every time there's an advantage, I almost always find there's a disadvantage. That's why the world needs, they need us to be critical thinkers to look at the balance. So what do I now do? Ed, I need this slope. If I'm going to push this higher to get more of the good signal, that's good. This slope has got to come down quick. And how do I design a filter with a steeper slope? I go for a higher order. So if I move this to maybe like the 800 region, I'm going to be like, oh, this is great. I'm getting all of that good signal. Now I'm getting too much noise. You might have to go to a 4th order or a 5th order or a 6th order to have that slope drop off quicker. That's the input. That I think is really interesting. That's the insight, not the input. That's the insight. How am I doing? Ryan, am I connecting? Am I making sense? So, but I don't get into this here. So I said to the TA, give full credit for any answer that's not too close to 936 and is at least equal to or higher than 637. We're good. If you understand this, that's great. You understand the secrets of designing filters. Now, what's the minimum sampling frequency of the A to D converter? The answer is 2 times the highest frequency. Okay. Now, this is where it gets a little gray. What is the highest frequency out of this filter? So in the book, the author keeps it simple. He makes it 2 times F sub C. But no matter what your F sub C is, you're still getting a lot of this signal until you're out a little further. So what you really want to do is say, look, at the absolute minimum, it's 2 times F sub C. But I know I'm still getting a lot of the signals above F sub C. So maybe I might want to sample a lot more than 2. And that gets you into determining the sampling. All right, so 2 times F sub C. We're on to question 7. Let me pause. How am I doing in this review tonight? Am I doing okay? We're all doing okay? We're doing all right? All right. Now, you have an N-bit analog to digital converter. All right, stop right there. N-bit A to D converter. That means each sample is converted to N bits. Remember, we sample and then we measure the height of the sample and convert it to a group of bits. An N-bit A to D converter means that each sample has N bits. Now, the highest frequency in the analog signal is F sub H. The sampling rate is 1.5 times the minimum. Determine an expression for how many bits are generated in capital T seconds. It sounds hard, but it is. It is. It sounds hard, but I think we're okay. What do we have? An N-bit A to D converter. In comes a signal. Highest frequency is F sub H. And we're going to now figure out how many bits come out per second and then multiply it by capital T, because that's the total number of seconds. So the absolute minimum sampling rate, as pointed out here on the screen, the absolute minimum sampling rate, 2 times F sub H. However, we oversample. That means we take more than the minimum. And the problem says we sample at 1.5 times the minimum. So the actual sampling rate is 1.5 times 2 times F sub H. That gives me the number of samples per second. How am I doing? So now that gives me the number of samples per second. And I think on this type of problem, if you follow the units, you'll get it. I have samples per second. I now multiply it by bits per sample, which is capital N. So I check out the units here. Samples per second times bits per sample gives me bits per second. Now, all I have to do is multiply that by capital T, because T is in seconds. So that's going to give me the total number of bits. And there we have, that's the answer. So that's how many bits are generated by this system, capital T. We're good, we're good. I'm looking around the room. Everybody's taking notes. Home audience, I hope I'm doing okay. All right. Next problem, problem 8. To determine the order of a filter. Just thought of something else I want to mention at the end of this video. I'm just writing it down here. Okay, I'll get it. All right. So now we have a sensor connected to a filter, and it's a low-pass filter of order N, unknown order. So we have to figure it out. So this is an exam 1 question. So the sensor has an output signal of 2,000 hertz. So to keep it simple, we select the corner frequency to be 2,000 hertz. Now, based upon our discussion, you might say, well, we really should pick it a little higher, but we'll for this problem, we'll keep it simple. So we picked the corner frequency to be 2,000 hertz. Now, it says up on top, in all these words up on the top, that there's a noise signal at 12,000 hertz. And we want that noise signal to be really as much removed as possible. And in particular, we want the gain of the noise to be minus 45 dB. Now, you might remember, we'll see it coming up, dB is a logarithmic measure. If I get a negative number, that means the gain is less than 1. So it's not a gain, really. You're getting out less noise, that's just what we want. So the first thing you have to do, because we're going to use a formula that we have to know the gain in non-dB, first thing we're going to do is to calculate the gain in non-dB. Now, this formula is given on the formula sheet. The gain in dB is 20 times the log to the base 10 of G, where G is the gain in non-dB. So I solve, and I get minus 45 dB. In this case, means that the gain is 5.62 times 10 to the minus 3. Now, there's a formula which we didn't derive, but my colleagues, and I know this is fresh in my mind because I'm working on the circuits final, that formula there should look familiar. We derived that formula in circuits for n equal 1. The magnitude of the gain is 1 over the square root of 1 plus f over f squared, that last quantity. Turns out, if you were to go through it for second order, third order, you just have to make the power be 2 times n. So what do I want? I want the gain to be 5.62 times 10 to the minus 3. Now, just be careful. It's f over f sub c. F is the frequency of the signal whose gain is going to be no more than 5.62 times 10 to the minus 3. That's the noise. So that's 12,000 divided by 2,000 raised to 2 times n. N's the unknown. My colleagues, the rest I'm sure you can do. I have, done it step by step. Make sure you can do this calculation. And notice n turns out to be 2.89. Christina, I know you know this. You always have to go up. Even if it was 2.1, you don't say 2. Because if you were to go back and put n equal to 2, you won't get the gain that you want. Okay, the gain will be too big for that noise. So you always go up. So 2.89 becomes 3. So would 2.1 become 3. So now you know that you need a third order filter to meet the requirements for this system. Some people taking notes. A moment break. We'll get the notes. All right. Are we good on this? All right. Now, the next one, loading error. All right. Help me out. Even before we look. What's loading error? If someone were to stop you on watching, say, okay, I can tell you're an engineering student. You look smart. What's loading error? And you would say it's V before minus VF. That's the loading. So I'm given a sensor which has a Thevenin equivalent model, and we connect to a 2-resistor network. A load resistor is placed across the R2 of the attenuator. Determine the loading error due to this load resistor. Let me draw the circuit for you first. That's the circuit. V Thevenin, R Thevenin. Now, if this was my circuits final, I'd have you calculate V Thevenin and R Thevenin, but not here. I give you, okay? And then I say we have a 2-resistor attenuator, R1 and R2. And we're about to take V out and connect it to something else, maybe a sensor or a meter or something. So what I need to do is to calculate V before and V after and take the difference, and we're done. So V out, now I'm hoping you are all very comfortable with this. This is voltage. V out is in the numerator, the resistor where you're measuring the voltage, and then divided by all the resistors in series. And you multiply that by V Thevenin, which is given to be 15 millivolts. So before we add any load resistor, the output is approximately 10.66 millivolts. Now, what do? I add the load resistor. Before I show you, I know you know how to do this. What is the only thing that's different? What do I have to find? If I put another resistor there where V out is, I hear people in the home audience yelling it out. I have to find an REQ. So I tell you the load resistor is 40 kiloohms. Now, before I can do voltage division to calculate V out, I can only have resistors in series. So here I have 2 resistors in parallel and no trouble. What I do is I just do an REQ. REQ, product over the sum for 2 resistors. So I get an REQ of 15.38. Now, I can calculate V after. So again, using voltage division, in the numerator, I put the value of the resistor whose voltage I am measuring. So it's 15.38 divided by the sum of all resistors in series. And in this case, I get 9.028. Notice, when you add a load resistor, you're pushing the voltage down. Okay? You're pushing the voltage down. So the loading is the difference. And I spelled before wrong. I never noticed that. So before minus after. So this minus this is the loading error, 1.63 millivolts. That's how much the voltage changes by adding that load resistor. How am I doing? Perfect, Alexander. So before and after means we're going to connect this load resistor to see what happens. So before you collect that load resistor, measure the voltage or determine the voltage. Now add the load resistor. This is now the after. Calculate the new voltage. You'll see that it always goes down. Did I do okay? So that is the loading error. Extra credit questions. We don't need extra credit. We're good. All right. I got 3 more things to say. First of all, how was this exam? Good? Now, 3 important announcements. I wrote them down over here so I wouldn't forget. First of all, for those of you who attended my lecture, I hopefully summarized Chapter 11 in 2 tables. Strong word of advice. Know those tables. Now, if you weren't at those lectures, find someone copied down. Right? So the first note I had was no binomial. The second note says for Chapter 11, know the 2 tables. All right? Fair? All right. Next, item number 3. I have only recently added IoT to this. This exam had no IoT questions. You should expect IoT. So what are some sample questions? Tell you what, I don't want to put anyone on the spot, but can anyone help me? What is IoT? If I were to ask you, describe, tell me, what is IoT? We have a brave colleague stepping up to the forefront here. Alexandra, what would you say? Perfect. I would go with that all the way. IoT is, a group of sensors. It could be one, but a bunch of sensors that have some type of connectivity, typically wireless connectivity, that then connect to the internet. And that then results in the collection of large data. So those are the kinds of things I would ask you. So how do you prepare for the lecture on IoT? Hopefully you attended that lecture. And then you could just go through the notes. Okay? I'm going to look at the notes and ask you a couple of questions on IoT. Okay? So that's not on this exam because this IoT is only a relatively new addition to the course. Good on IoT? Okay. Last item, short answer questions. Remember the short answer questions from exam 1? I think we had some on exam 2. I would look at them. Now also, the chapter 11 questions with the tables, those could be short answers. IoT, as Alexandra just helped us, that is short answer. There was also, I wrote it in my notes, IoT equals. I think I had 5 things. IoT equals. Now let me see if I can remember these 5. Sensor, wireless connectivity to a network, the storage of data, and the controller. I think I might have said controller that does the analytics. And then there was an actuator. Remember, we used the example, maybe an actuator might inject medicine into someone who needed it. And the 5th item was an identifier. Now, Alexandra's checking her notes. How did I do? Good? Do I get an A? An A+. I love it. All right? So, my colleagues, again, just to summarize, no binomial. Chapter 11, know those tables. Go over the IoT lecture notes. Expect short answer questions. And in general, even though this final didn't have them, I might ask you questions maximally flat. Exactly. Butterworth. You all got it. Perfect. What's the number 1 source of systematic error? Exactly right. I heard the home audience say it. Lack of calibration. So just be ready. I might hit you with a couple of jabs. All right? So short answer question. That should do it. I apologize for the mistake I made earlier tonight. I have no excuse. Too much on my mind, but that's a bad excuse. Hopefully I've recovered from the mistake and everything's okay. Are we good? Did we achieve tonight's goal? Jesse, as always, you and your colleagues at SIT TV, thank you. Good night, everybody. Thank you for showing up, everyone.